All right, welcome back to trigonometry. So today we are going to talk about inverse trigonometric functions. All right, so what I mean by this is like we usually have like a sine of some angle gives us some ratio. Okay, sine of x equals y. So you have to think. I usually write my angles like as a theta just so that I can remember like what's going on with this. The idea here is we're going to say what angle, or if we have a ratio, okay, what angle led us to that ratio? Okay, and there's two ways that we write this. We can say that the theta is equal to arc sine of y, or sometimes we say sine inverse. Okay, I think the modern calculators generally like to use the theta equals sine inverse, but you may see older books where they're going to use arc sine just because when it's a little negative one up here is a little bit was awkward for early typesetting. So that's why we didn't do it. Okay, this does not mean the reciprocal. Like the reciprocal of sine is cosecant. This has nothing to do with cosecant. All right, these are inverse functions. So the idea is I'm going to give you a ratio, and you're going to tell me what angle led us to this ratio. So, for example, even though I did not require you folks to like go ahead and memorize your unit circle, we've done a couple. So I could say, what is the inverse sine of, say, I want a ratio. I want the square root of 3 over 2. Okay. And you say, okay, what angle would lead us to that? You say, oh, well, theta, that's going to be pi over 3 is going to give us square root of 3 over 2, right? We can check it out. Sine of square root of 3 over 2 equals 0.866 and a dot, dot, dot. But that's also going to be the square root of 3 over 2. Okay, so that's what I'm asking you to do is like, here is a ratio, and then give me the angle that this ratio came from. Okay, the sine of this angle that the ratio came from. Okay, so that's like the main idea of what's going on here. All right, let me think about what I'm going to do next here. Um, One of the things about inverse functions, so if you're in pre-calculus, if you've gone through, you've probably had a unit on inverse functions at this point. And one of the things that we tell you about inverse functions is that it must go ahead, it must pass the horizontal line test. Okay, so I'll ask you, does sine pass the horizontal line test? Like, well, of course it doesn't. You just draw a horizontal line through it and pass through it two times. No, it doesn't. Like, good, it doesn't. So we have to restrict our domain with inverse sine so that we actually get a function that passes a horizontal line test. So the way we do this is we kind of restrict our domain so that we are going to be between negative pi over 2 and positive pi over 2. Okay, so the only angles we're going to get, right, when I say theta equals the inverse sine of some ratio, okay, it's got to be between negative pi over 2 to positive pi over 2, right? Which means if you're working on an application where you know that the angle is going to be in, say, the second quadrant, inverse sine ain't going to give you that angle. You're going to have to use your own brain to figure out, oh, what angle is that actually working towards? And that's how we're going to use reference angles. That's why it was important that we learned reference angles earlier. Okay, so one of the things that I'm going to do is I'm going to show us a little bit of a picture of the inverse trig functions so you can see what the graphs look like. Now, unlike the regular trig functions, we don't really care if you're able to graph inverse trig functions very well, with one exception. Okay, and that exception is inverse tangent. So let's go ahead and graph these things and we'll see what's going to happen. Okay, so if I have my sine table here, and we're going to say we need negative pi over 2. We don't have to do all of them. Negative pi over 4, 0. Let's go with pi over 4, and then we'll say pi over 2 here. Okay, and that, again, this is the range of angles that I am allowed to get out of this. Negative pi over 2, sine of negative pi over 2, negative 90 degrees, it's going to give me negative 1. This is going to give me negative square root of 2 over 2, which is negative 0.707. Sine of 0 is 0. Okay. Sine of pi over 4 is square root of 2 over 2, which is also equal to 0.707. And then we have sine of pi over 2, and that gives us back to 1. So remember that when we did inverse functions, when we were constructing inverse functions, one of the first moves we made was to swap the x's and the y's. And that's exactly what I'm going to do when I go to show you the picture. So instead of saying x to y for sine, I'm going to say x to y for inverse sine. Okay, so as I'm looking at this picture here, we have my x's are, we have x is -1. Okay, so here's -1, here's +1. My y is -pi/2. That's all the way down here, like -1.57. That's -pi/2, right? We do -pi/4. I don't know what pi/4 looks like, but let me go ahead and do my handy dandy calculator here. So pi divided by 4, okay, is about 0.78. Okay, so we're going to be about here, 0.78. And we're going to be down here at zero point 0.7. Okay, so here's 1. Here's 1. Okay, we're down here at 0.7. So I'm going to have a point right here. I'm going to have a point here. Okay, 0, 0. My x is going to be 0.707, so I'm here, right? And my y is going to be, I'm sorry, my x was going to be what I just said, which was, what am I looking at here? 0.78. Okay. So we'll call that 0.78. And my y value is going to be 0.707. So we're going to be up here. Here's 1. We're going to be up here somewhere. Okay. And finally, when I get my x value to be 1, my y value is going to be pi/2 or 1.57. We're going to be up here. Okay. So let's see if we can draw this guy in a little bit carefully. Okay, so that's kind of a very rough graph of what inverse sine looks like. This is y equals inverse sine of theta. Okay, or y equals inverse sine of x, x being a theta, x being an angle. Okay, and that's what this thing kind of looks like. All of the regular graph transformations that you have learned in Algebra 2 or in college algebra, they all still apply. So we can move this around, horizontally. We can move it up and down. We can stretch it. We can shrink it. We can reflect it. We got all sorts of graph transformations that we can play with this thing. Okay. Cosine, we're going to do the same thing with cosine. All right. Now, cosine is a bit different. So we're going to say, here's my x, here's my y for cosine. Okay. So for cosine, let's go ahead and look at what cosine looks like. Cosine, something like this, right? It goes in both directions. And again, it fails the horizontal line test, right? We're not going to have a chance for this. So if I go through and have this, like, oh, look at that. It failed the horizontal line test. Well, of course it did. We just kind of talked about that and how that's not going to work for us. So for cosine, for inverse cosine, we're going to restrict our domain to a place where it won't fail the horizontal line test. So the theta for the inverse cosine, right? Again, we're feeding inverse cosine a ratio and it's spitting back an angle for us. And this angle is going to be between 0 and pi. Okay, and that includes it. Okay, because those are defined quantities and that's fine. If I go ahead and put in cosine of pi, I will get -1, and it's okay. We can go backwards from that. So we're going to be inclusive with our angles. So those brackets are appropriate. Okay. So again, since we have to go from 0 to pi, so if I'm looking at this for cosine, okay, so here we have cosine of x. So we can say, okay, 0, and I'll use some very similar angles, pi/4, pi/2. We'll do 3 pi/4, and pi, and we'll see what those are. Well, cosine of pi is -1. Cosine of 3 pi/2 is going to be -√2/2, or -0.707. Cosine of pi/2, 0. Okay. Cosine of pi/4, that's going to be the square root of 2/2, or 0.707. Cosine of 0 gives us 1. And again, just like we did for the inverses, if I change this to inverse cosine, then we're going to change this to an x. So you know what? Let's do this. I got colors. Let's play with colors. Okay. We're going to go ahead and change this to an x. And now this turns into a y. Okay. So we're kind of reading it backwards here. Okay. So we're reading it this way. These are now my x's. These are now my y's. All right. So let's see what that's going to look like. Okay. So we can go ahead and think about that. So when x is 1, y is equal to 0. So we come over here, x is 1, y is 0. When x is pi over 2, or sorry, square root of 2 over 2, so 0.707, y was 0.78. So we're going to be up here somewhere. Okay. When x was 0, we're here. Y is equal to 1.57, pi over 2. We're going to be all the way up here. Okay. When x is negative pi over 2, negative 0.707, we're on the other side of the axis here, other side of the origin rather. My y value is going to be way up here, right? 3 pi over 4. And when we have negative 1, it's negative 1, we're going to be all the way up here at 3. Okay, so we're going to get a function that looks like this. If you want to get a much better picture of this thing, please use Desmos. They are capable of drawing a much, much better picture than I am. But again, this is the picture of what inverse cosine looks like. And for as much emphasis as we gave you to be able to graph cosine and changed all of the horizontal stuff, the period stuff, the phase shift, the amplitude, for as much trouble as we gave you for that, we don't really spend a lot of time graphing inverse sine functions or inverse cosine functions. So that doesn't have nearly the kind of requirement that your original functions did. Now, the only one that's interesting, the one that we really, really care about is inverse tangent. Okay, and inverse tangent. So if we look at y is equal to the tangent of x, right, we have negative pi over 2 to positive pi over 2, right? We have asymptotes. Okay, asymptotes. So we're going to be doing something like this. We're going to be doing something like that. So I'm going to ask you from your pre-calculus days, the exponential function y equals e to the x. Okay, this had horizontal asymptote. When we graphed the inverse function, y equals natural log of x, what happened to that horizontal asymptote? Well, it turned into a vertical asymptote. Right? That's going to be the same thing here. We have vertical asymptotes turning into horizontal asymptotes. So y equals natural log x, we have a function that looks like this. Okay, we have a vertical asymptote instead of a horizontal. So the same thing is going to happen. So when we go ahead and graph y is equal to the inverse tangent, right, we're going to end up with a graph that looks something like this. Okay, so we have pi over 2 here. We have negative pi over 2. Okay, and we're going to go ahead and draw our horizontal asymptotes here. And then we're going to have our, uh, it doesn't actually cross, I'm just a terrible artist. Okay, and then here is our inverse tangent. So my tan inverse of x looks like this. The reason why we think this one is interesting is because it is the only function that I know that just has organically occurring two horizontal asymptotes. Now, I can construct a function that has two horizontal asymptotes on it. I'm going to have to make it a piecewise function in order to do that. So you're going to know something is up, and I'm up to something sneaky trying to do this. So you're going to see the piecewise function. But inverse tangent, a little different because it just organically has two horizontal asymptotes. They don't cross each other or anything like that. Okay, so that's why this one is actually a pretty interesting function. This is why you kind of have to know this one. As far as solutions that you're going to see, getting an inverse tangent in like a railroad solution happens pretty frequently. Having to graph like inverse sine or inverse cosine, that doesn't happen all that often. Okay, it's nice to know that there is a graph, and it's nice to know that we can't graph it, but they don't come up all that frequently when we have to go ahead and do graphs. Unlike inverse tangent, which does come up a little bit more frequently. Okay, mostly because it doesn't have a restricted domain, right? The domain here goes from negative infinity to positive infinity, whatever you want. It's got a restricted range, but we don't care so much about that. So inverse tangent is a really important one to be able to deal with. I think I know that Desmos does know what inverse cosecant is and inverse secant. Those are some pretty crazy looking functions. I will also tell you that some books graph them a little differently than others. So there isn't a 100% compliance on how this graph should look. Like some people want to put the graphs together or they want to do something with them that kind of changes how they look because they changed how the order goes. But for the most part, I mean, Desmos is like the 99% consensus, but There are some books that will have a different picture of what this thing looks like, which is one of the reasons why we don't have you graph inverse cosecant and inverse secant or inverse cotangent. I mean, I barely had, wow. So we don't really worry too much about those functions, the inverse functions, the reciprocal functions. But as far as like which ones to memorize, inverse tangent is definitely the one you have to memorize. The other two, it'd be nice to know that you kind of remember what they're supposed to look like. And the fact that they have this truncated domain means that we're going to have a truncated range. Okay, so you can go ahead and look at it that way. Okay, so with that, we're going to do some examples of some numerical examples next time, but I think this was probably long enough. So thank you very much for watching, and I will see you in the next video. So stop sharing and stop recording.